Welcome back to Calculus 1. We're going to continue our journey through the beginnings of integral calculus in this lecture and finally get to the question of how we're going to find the exact area beneath the graph of a function over an interval. Our last lecture, we dealt with approximating this area by using rectangles. Now we're going to get to how we'll find the exact area. All right, in our last lecture, we had our basic problem. Given the graph of a function over an interval a to b, how can we find the area beneath that graph and above the x-axis? Well, as it turns out, that requires a little bit of work. We start by approximating our answer, trying to get an approximate area, and we can do that by approximating with rectangles. And if you think back to our last lecture, the way this worked, we choose a number of rectangles that we're going to use. Typically, if we're doing it by hand, like we would ask of you, students, to do, we choose a small number. Here in the sketch, looks like we have 6 of them. We can calculate the width of each rectangle, or alternatively, we split the interval a to b into that many subintervals. And then we can pick a point within each subinterval to determine the height of each rectangle. And then the way we'll calculate the area is the function value at a certain endpoint. The function value represents the height. Multiply that by the width, delta x. Height times width gives you area of one rectangle, and then we sum them up. So here, with that sketch, we drew it with 6 rectangles. And if we choose to use the right endpoint approximation, using the right endpoints of each subinterval to determine the heights of each rectangle, we get this expression. All right, now we might be interested in how we find the exact area. And what we hinted at in the last lecture, we typically approach problems within calculus by trying to first get an approximate answer, and then we refine or make that approximation better using some sort of limit. We're going to see that here. You might recall from our last lecture, we mentioned that we can get a better approximation by using more rectangles. And in this lecture, we'll take that to the extreme by using basically an infinite number of rectangles. Now, before we move on, just to get some notation out of the way that we'll be getting to momentarily, notice the way I expressed the right endpoints. Here, we're just keeping it labeled kind of as arbitrary values along the x-axis. We have a left endpoint A and then a right endpoint B. The individual subintervals, we have them labeled coordinates x1, x2, x3, x4, x5. So if we're splitting that interval into 6 pieces, you'll have 6 right or left endpoints, 6 subintervals. Now, for this example, we chose to do it using a right endpoint approximation. And if you take a look at your interval, a to b, the very first subinterval is that interval from a to x1. That first right endpoint that we choose, what we're labeling as x sub 1, we add to our left endpoint value a, the width of that subinterval is delta x. So x1 is a plus delta x. Now to go from x1 to x2, the next subinterval, we add another length or width of delta x. So x sub 2, the second right endpoint, would be a plus 2 delta x, and then so on and so on. Recall, we split up the interval into subintervals of equal width. Okay, so let's go ahead and get to answering the question at the bottom. How are we going to find the exact area? We use more rectangles, take that to the extreme. We're going to set this up as a limit as the number of rectangles goes to infinity. All right, now we're going to introduce something called the definite integral. And as it shouldn't be any surprise, things in calculus, derivatives, and now integrals kind of have at their foundation a limit definition. Now we're going to get into kind of a way to write that. It's not going to be convenient to write by hand. since it introduces something called summation notation. So we'll take a little brief interlude on that, and then we'll go back to answering the question of how we use a limit to define the definite integral. Now, you might have encountered summation notation maybe in a previous, let's say, pre-calc course. Chances are maybe not. So let's go ahead and introduce it, basically just so we can write down some standard calculus notation. So what summation notation is, it's a convenient way to write down sums that involve a large number of terms. For instance, if you're adding up 100 different things and they all have a pattern, chances are mathematically you would write that using summation notation. That's relevant to us and our problem of approximating the area because we add or sum up a bunch of rectangles and their areas. So let's take a look at a very general version of what summation notation is. The standard symbol is the capital Greek letter sigma there. And there's a few different parts of the notation I just want to make sure you're comfortable with. So at the bottom of that summation or sigma sign, there's I equals 1. We refer to I as the index. It's just a symbol. Could be any variable, for instance. I, N, or K are the typical indices that are used in mathematics. The 1, what I equals, that is assumed to be the starting index value. And here, typically, we're going to start counting things with 1. And with summation notation, the index always changes by 1 unit. So here, if we start our index at 1, the next index value would be 2. After that would be 3, then 4, 5, so on and so on. It's basically due to how we count things. We count usually a whole number amount of things, counting 1 unit in between. All right, and at the top of that summation sign is N, and this is denoting the ending value for the index. The part to the right of the summation or sigma sign, A sub I, this is what's referred to as the general term that is indexed here with I. All right, now this is all maybe new, but what does this really mean? Well, we just start this general term with index value 1. So basically in that expression for the general term, some sort of formula, we just replace anywhere there's the index, in this case I, first with the value 1. And here it's only in the subscript, so we get A sub 1. We then increment the index to the next value, 2. We plug in, I is 2, and we get A sub 2. So basically this is just labeling the finite sum of n different real numbers, A1, A2, A3, all the way up to A sub n. And we just add them up. Okay, let's take a look at some examples, again, assuming no familiarity with summation notation. Let's say we're looking for the sum from the index value 1 to 10 of the general term I. Now be careful here, I is referred to as the index. We're not assuming it is square root of -1. All right, so if we write out what the terms are here, we start with index value 1 in our expression, and our general term, A sub I, just equals I here. So basically what we're doing is summing up the numbers from 1 up to 10. So our finite sum here, written in summation notation, is just the sum of numbers 1 plus 2 plus 3, all the way up to 10. And if you add them up, sum that up, you'll get 55. And that's a simple formula for the general term A sub I. A sub I, for example 1, is just I. For example 2 here, A sub I, the general term, is I squared. So maybe give yourself a few seconds to see if you can write out the terms here, and then we'll continue from there. All right, unlike example 1 where we were summing the natural numbers from 1 to 10, here what we're summing are the squares of the natural numbers. from 1 to 5. So we basically just add up, start with your index value, I equals 1. You have 1 squared. Then we increment to I equals 2. The general term gives the value 2 squared. Then we increment I to 3. The general term gives 3 squared. Usually after a few terms, you can see the pattern. So we're just basically adding up 1 squared, 2 squared, all the way up to 5 squared. And by pure coincidence, this also has the same sum there of the squares, 55. All right, now before we move on to tying this into the approximation of area with rectangles, I feel compelled to pass on some mathematical history and mathematical lore. Every good math professor should do this. And it deals with that kind of first sum there. Now adding up the first 10 numbers. Now legend has it that the world-renowned mathematician Gauss, there were some famous mathematicians like Gauss, Euler, Newton, whole bunch of others. And legend has it when Gauss was in elementary school, kindergarten, first grade, we're not sure, he was so brilliant that his teacher got annoyed and just basically sent him off to the corner and said, fine, go add up the first 100 numbers. And Gauss came back within seconds, as again, legend has it, and he gave the correct answer, 5,050. Now he did it in a very slick way. What he noticed is if he takes that sum from 1 to 100 and then flips it around and adds it to itself, notice each pair, just kind of written vertically there, 100 plus 1 is 101. 99 plus 2 is also 101. What Gauss noticed, again, why he's a mathematical genius and world-renowned and one of the greatest mathematicians of all time, is that each of those pairs sums to the same number, 101. So he was really clever and came back seconds later and noticed I have 100 101s. We're adding up the same number, 101, 100 times. Repeated addition is multiplication, but we added the number, the sum to itself twice, so we divide by 2. So we get the sum, 100 times 101 divided by 2, which is the correct sum, 5,050. All right, completely unrelated to the course, but again, important to pass on mathematical lore. Let's go ahead and tie summation notation back to what we really were bringing this up for, a way to kind of transition from approximating area to finding the definite area, exact area with a definite interval. Okay, now we introduced notation. It's just a way to write this down. It's not anything other than that. There's no concepts really involved in summation notation. The concepts are here with what we kind of thought of in the last lecture as the outline for how we're going to tackle finding the exact area beneath a curve. And this follows the outline of a lot of problems in calculus. We start by finding an approximate answer, and we do that by approximating the area with rectangles. And once we have the approximation, we refine it and make it better, and that's almost always within calculus by using a certain limit. And what we're going to be doing is using a limit as the number of rectangles increases to infinity. All right, so let's kind of visualize this just to see how this works. We'll introduce some notation and tie this into summation notation that we were mentioning a few minutes ago. So let's say we have this curve here. We're only considering the curve or graph over the interval of x values from a to b. We choose a certain number of rectangles. We'll keep it abstract. We'll say n. And then we calculate the width of each rectangle or subinterval. Delta x, defined as b minus a, the length of the interval, divided into n pieces. All right, so let's not try to sketch all of these, just incorporate summation notation. Let's go ahead and focus just on the interval a to b, which we are partitioning or subdividing into n different subintervals. I'm not going to label them all, but imagine this could be a small or large number of intervals or rectangles. We're just splitting that up into n of them, all of equal width. All right, just for consistency, we're going to give our limit definition for the definite integral, which we're working up towards, using right endpoints. All right, and if you take a look at all those subintervals, your first right endpoint for the subinterval a to x sub 1, the first right endpoint, x sub 1, is a plus delta x. From the leftmost value, a, we add 1 with delta x. To get to the next right endpoint, x sub 2, we add 2 with delta x. X sub 2 is a plus 2 delta x. And to get to basically the nth, or here ith, subinterval and its right endpoint, we just multiply the width by however many intervals we're moving along, I, and then add that to a. Okay, now all these values, x sub 1, x sub 2, x sub 3, so on, up to x sub n, remember we're choosing n subintervals, so we don't have to count beyond n of them. We're going to use those to determine the heights. So we plug in those right endpoints to the function. That gives us the height of each rectangle, f of x sub I. Again, that represents the height of each rectangle. And then we multiply each of those function values at right endpoints by the width, delta x. The area of one rectangle is written down there, f of x sub I times delta x. Now, if we choose a very large number of rectangles, for instance, let's say 100, 1,000, maybe more, we don't want to write 1,000 or 100 different function values times delta x. This is where summation notation comes in. We can just represent that as this really compact expression for any finite amount of rectangles. We write it as the sum from index value 1 to n of the general term f of x sub I times delta x, where we have those right endpoints defined above, x sub I equals a plus I times delta x. And we basically sum over that, counting all your right endpoints from 1 all the way up to n. Here, x sub n, your last right endpoint, is the rightmost endpoint of the interval b. All right, so what we have here is a standard way to write the right endpoint approximation. It's written in summation notation. And now, kind of coming anticlimactically, we can basically give the answer to how we'll define the exact area. We take a limit of this as n goes to infinity. And there it is. The exact area. It's not really pretty, but again, beauty's in the eye of the beholder. We have it here. So once we write down our right endpoint approximation, you could also use the left endpoint approximation. Once you write it down in summation notation, we just take a limit as n goes to infinity, as the number of rectangles increases to infinity. Now notice where the n appears. N appears at the upper index of the summation, and n also appears in delta x. The width was defined as b minus a divided by n. So two things are happening as n goes to infinity. You're adding up more rectangles, but they each become narrower. Okay, what we have just defined is this new fundamental tool in mathematics and calculus called the definite integral. A lot of things at their foundation in calculus are defined as limits, which is exactly what we have here. We define this thing called the definite integral of a function over an interval a to b. It is that limit expression the limit of the sum of all those rectangular areas. All right, so again, at its heart here, this new tool, a definite integral, is defined as a limit. Now think back earlier in our course when we defined derivatives as limits. We didn't really use the limit definition much for a few examples, but it was our foundation. We're going to do the same thing here. We have our foundation now for definite integrals, a way to find the exact area, but it's really, really not practical. Nobody evaluates integrals using this limit as the number of rectangles goes to infinity. We're going to have some other tools that we'll be getting to, and you'll continue on learning in Calc 2 if you go to that. But let's go ahead and continue with this new thing called the definite integral. So the wiggly, what is called the integral sign on the left there, this was chosen to look like an elongated S, representing summation. So we refer to that squiggle as the integral sign. A and B are referred to as the limits of the integral. Be careful, we're using limits to refer to A and B on the integral sign. The definite integral is also defined as a limit as n goes to infinity. So it's unfortunate that the same word, limit, is used in two different contexts here. All right, the other thing which is worth pointing out, it's kind of at the foundation of why calculus took a while to develop. Delta x, think of that as a finite or measurable width. We defined delta x as b minus a divided by n. And that's something that you could measure. Maybe it is small, like, centimeters, millimeters, nanometers, but that is still something measurable. Now, what happens to the width, delta x, as the number of rectangles increases? Well, notice, since the n is in the denominator, the width is going to get smaller and smaller towards 0 as n approaches infinity. This is a little bit bizarre. We don't let delta x precisely equal 0, but we let it get really, really close. It's almost 0, but not quite. And this is a new concept, what's called the infinitesimal width. It is a mathematical concept, kind of like infinity. Infinity is a kind of useful concept for things that keep increasing. Here, what we're calling infinitesimal is the opposite. It's infinitely small. Don't assume dx equals 0. It doesn't, but we stop just short of that. And that's really bizarre to consider a number that is not 0, but the next biggest number than 0. Normal real numbers don't fit that, but this leads you to kind of an alternate way to define calculus with things called hyper real numbers. We're not going to go down that route, but you could. So just think of delta x as being the width, dx as being the infinitesimal width. All right. Now, before we move on, just to give you a solid foundation, especially for those of you moving on through the rest of the calculus sequence, maybe into Calc 2, 3, 4, maybe some of you moving through the entire calc sequence all the way up to Calc 27, it might be good to see how there's a parallel between defining derivatives and defining definite integrals. All right, so let's go back earlier in the course. We had this limit definition for the derivative, f prime of a, and we started by finding the slope of the secant line, which was our approximation, an approximation to the slope of the tangent line, and then we make our approximation better. Back then, earlier in the course, that was taking a limit as h goes to 0. Now the derivative, as we defined it, is incredibly useful to calculus. It's what we've done the entire course with up until the past 2 lectures or so. And we have a similar limit definition now for definite integrals. It's a little more awkward and abstract, but there's an approximation which we have here written down the approximation with right endpoints. And then we refine that approximation by now taking a limit as the number of rectangles goes towards infinity. So if you're continuing, especially into higher level mathematics, it's important to see that at their foundation, concepts in calculus are defined as limits. Now, for those of you really not moving on through the calc sequence and just maybe ending with this course or Calc 2, we're going to get to some practical tools to evaluate this, as might be needed for your science, engineering, or business courses. And we're not going to use a limit definition. It's more or less for mathematical consistency. All right, before we move on, let's get to a really simple first example to kind of tie this into the main question: how do we find exact area? And now we can. Exact area, area beneath a curve, we can calculate that as this new tool that we're calling the definite integral. So let's take a look at a simple example here. Let's say we have a function given by its graph. Don't worry about an equation for the function here. And we're just simply asked, evaluate the definite integral from 0 to 5. All right, now this actually can be done very easily. It's actually going to be a whole lot quicker to get the exact area, as we're going to be doing here, than it does to compare it with approximating the area. Even if you were to pick a small number of rectangles, 4, 5, 6 rectangles, it's going to take you a few minutes probably to kind of calculate the width, function values, sum them up, waste of time. We'll be able to get the exact area really quickly, since this function has a really simple structure. It's a straight line segment and then a diagonal line. We can kind of think of this region beneath that graph as being the triangular area plus a rectangular area. And if we split that up, from the interval 0 to 2, we have a triangle. The base length is 2, the height is 2. We can get the area beneath that diagonal line as just basically area of a triangle, 1/2 base times the height. Now the remaining area beneath that curve is the rectangular region over the interval 2 to 5. 2 to 5, that's 3 units, 5 minus 2. And then that is the kind of the base length for that rectangle. The height is then 2 units. And just multiply, 3 times 2, 6. And we just add them up. This region is built out of a triangular part plus a rectangular part. You should get your total area beneath that curve as 8 units. Really quick, provided we interpret a definite integral as area beneath the graph. All right, now we're going to be kind of getting to in a little bit what happens if the graph goes below the x-axis, but that'll be saved for a kind of what comes next. All right, now before we get to that, let's take a look at some challenging examples. I think example 1 maybe primed you, got you ready for example 2 here. Example 1, you were given the graph, and it was pretty straightforward. What I'd like you to do here, the question is asking to evaluate each definite integral. Currently, we don't really have any tools or shortcuts at our disposal to evaluate definite integrals. Don't use the limit definition. Don't try to split this into an infinite number of rectangles and then add them up. I'll give you a hint. Try to think for each of the functions inside the integral. Think of what their graphs look like. Part B is a little more challenging. It stretches your kind of maybe familiar or unfamiliar mathematical knowledge, but we'll check in a few minutes. Use the hint, think of the graph of each function, and think back to example 1. Maybe you can think of the graph and visualize it as simple geometric figures, and you can calculate those geometric figures areas. We'll check in a few minutes. All right, welcome back. Now, part A is definitely the simpler one here, and it's probably simpler because between the two functions, absolute value of x and square root of 1 minus x squared, chances are absolute value of x, its graph, is more familiar. All right, so your absolute value shape is the standard V-shaped graph. And we're looking at that graph over the interval from -1 to 4. And we kind of get these two triangular regions. The area beneath that entire graph is built out of a small triangle on the left and a larger triangle on the right. So this area beneath that graph, this definite integral, can be split into two triangular regions. Notice the length of the triangle on the left. Be careful, we're covering a triangle on the negative x-axis, but since the graph is entirely above the x-axis, it looks like a normal oriented triangle. The base length going to the left is 1 unit, +1. The height, because it's above the x-axis, is also +1. So our triangle on the left looks like it has area 1/2 times the base 1 times the height 1, which should be a half. The triangle on the right has base length and height both equal to 4. So that's where the 1/2 times 4 comes in. And if you add that up, those two triangular regions, you get 8.5, 8.5, 17/2. All right, now part B is a little trickier, but probably only because the graph of this square root function is not as familiar. All right, well, what we have defined here is the standard way to express the upper half of the unit circle. Over on the right in red, just to build your foundation in case this was unfamiliar, let's start backwards with the equation of the unit circle, x squared plus y squared equals 1. That should at least be familiar from your pre-calculus course. And we can solve that for y. First subtract x squared, and then undo the square for y squared by taking the square root of each side. Now be careful, when you take that square root, you have to append the plus or minus in front to account for both square root values, the positive and the negative. That square back to 1 minus x squared. The positive root gives you the upper half. The negative root gives you the lower half of the unit circle. All right, with that kind of out of the way, now maybe you see how this square root function relates to the unit circle. The question becomes rather simple. Just draw a circle, take the upper half, and the definite integral, we're still interpreting it as area beneath the graph over that interval -1 to 1. So pretty much all we need to recognize here is the area beneath this curve is that for half the area of a circle. And if you recall the basic formula for area of a circle, pi r squared, since this is the unit circle, the radius is 1, plug that in, we get the area of that circle of radius 1 as pi, but since we're just dealing with the upper half, we take half of that. So we get the value for our integral here as 1/2 pi, or pi/2. All right, now here, this didn't require anything other than a geometric interpretation as the area beneath the curve as a familiar or unfamiliar geometric figure. What we'll be getting to kind of next, in the next part for this lecture, is the question of what happens if the graph goes below the x-axis. So far, all the examples that we've kind of used in sketches and examples, the graphs have been entirely above the x-axis. So part 2, which picks up right at this point, right after this, delves into, well, what if the graph goes below the x-axis?